Yeah, actually, there in the title there wasn't a question mark. The question mark was a mistake in the communication. So we are doing it, so it's not a question. All right, so this is Chai from Cruise. Very excited to be here. And before I start, I'd like to thank the wonderful organizers of this workshop for this opportunity to speak here today. For this talk, I thought we'll discuss a few things. Namely, I'll talk about a few projects that we've been doing at Cruise Research, and I'll also highlight a few directions that I like to have the academic community and the industry community moving forward as far as self-driving is concerned. All right, so just for our international audience, just a few words about our company. We are a company based in San Francisco. We specialize in building self-driving cars for ride-hailing and delivery services. And has been, the company is about 10 years old. And we are, so here's just a short video. I'll just play it here while keep talking. So we actually deployed a self-driving fleet and operation in San Francisco and beyond. And as you can see, we can handle very complicated situations in San Francisco. I think for one of you who have been in San Francisco, especially during nighttime, it's a complicated, it's a lot of interesting things happening in San Francisco. And the fact that we have an operating fleet in the city speaks for itself. And so I also wanted to talk a little bit, just a few words on how we are thinking about scaling the self-driving car operation. So again, right, we started in 2021 with just 2 cars covering about 30% of San Francisco, and we were mostly operating during nighttime. And then around CVPR time last year, we scaled to tens of cars covering 70% of San Francisco. We were still constrained at nighttime, but then already at New York's time, we scaled to over 100 cars covering most of San Francisco during nighttime and somewhat during day as well. And back then I said, okay, hopefully we'll be covering the full San Francisco soon. And this is indeed the case. If I were to, can I move this thing, this block here to somewhere else? Yes, perfect. So that's indeed the case if we look at where we are now. So we are in 2023, June, we have, hundreds of cars driving in San Francisco. If you were to visit San Francisco, maybe after this workshop and conference, you'll see our cars driving in San Francisco. You'll find many of them. And we've also scaled to other parts of the US. It's Phoenix and Austin. And we also always had the belief, if we were to be able to tackle San Francisco, the other cities in the US are a lot easier to handle. And that turned out to be indeed the case. In Phoenix and Austin, a lot of roads, they are much wider, fewer pedestrians, fewer bicyclists, and, just a lot easier. So we were able to scale really well. And yeah, I think I just want to remove this, and we are, okay, now it's on the left side. So I really can't. Oh, much better. All right. So, and we are doing it at 24/7 as well. Okay. So last slide here, we are now looking at new expansions in Dallas and Houston, and those are some of the largest cities in the US. And we are also looking forward to deploying in international markets such as Dubai and Japan, and deploying our customly built hardware that's just for the self-driving car application. All right, enough about the company. I'm pretty sure you folks are here to listen about technical details rather than business. The next few slides, I just want to outline a few kind of research opportunities I see for the research community here and also our industrial partners. So to understand that, we need to look at how the self-driving car industry moves forward. And I think this slide not only applies to us, but it also applies to a lot of other self-driving car companies, right? Beyond even the ones working on L2 and beyond. So essentially what happens is you have some kind of self-driving car stack You put it on road and you gather problems. And that's where you see, you know, all those safety drivers in the cars, they gather problem, they make nodes. And, you know, those nodes, they go into kind of a database. People then, you know, engineers will then work on problems, and then they create solutions, retrain models, and redeploy models. So this is, you know, a typical iteration of the self-driving car stack. So then the question is, you know, these days, what are some of the hottest areas in machine learning? I think, you know, today we've already visited many of them. I think it starts with foundation models, also, you know, generative AI and so on. So I think, obviously, there's a lot of opportunities to use foundation models to optimize this pipeline. And it starts with, you know, reusing some of the existing foundation models, like, you know, public available ones, like CLIP, like SAM, where, you know, you have a model that has seen basically the entire internet. And there are many ways to leverage those. And in particular, I want to point out in terms of auto labeling, right? When it's kind of expensive procedure that you can use, you know, some of these existing foundational models to do auto labels. But at the same time, you can also try to build your own foundation models. And I think today we've seen a few examples. We've seen, I think, you know, Wave has pointed out in this Gaia work, and I think, you know, Sergey talked about their foundation models as well. So then here's also the aspect of generative AI. I think these are very correlated, right? Here we talk about diffusion models, we talk about you know, autoregressive models, that's like GPT style models. And we also talk about even more traditional ones like GANs, like VAEs, they still have a lot of value here. So you can use those for, you know, for example, training data generation, especially if around long tail problems. And you can also use them for testing. I think, you know, as we heard from the previous talk with the new plan challenge, you know, the evaluation of planning modules is still extremely difficult. It's still, you know, if you want to get the diversity, you need to find counter factual outcomes for your planning stack. So all these generative models will be very helpful here. So finally, I mean, we are at the end-to-end workshop. So I also wanted to just give a shout out for kind of end-to-end solutions. I think it's not a secret that you know, a lot of you know, that end-to-end solution. There are, you know, a lot of companies, a lot of more mature companies that use like a more modular stack. But I do believe, you know, end-to-end solutions, they do have a place in the self-driving car stack, especially if we want to target particular maneuvers and functionalities that are, you know, maybe difficult to build and difficult to scale if you were to do it modular. But having mentioned all those opportunities, I understand that we've already listened a lot, listened to, you know, many talks addressing these three topics before, you know, over the course of today. So I wanted to give another perspective. I want to talk about like two areas that are a little bit orthogonal to you know, the three areas I mentioned before. So, and those have not been targeted. So on this graph, that have not been targeted by the other ones, other topics before. So one is around testing. So we talk about this workflow of, you know, finding problems and then, you know, tackling them one by one. But this is, when you think about it, if you really want to scale, this is not really a scalable approach. So you're essentially driving around and you're waiting for problems to happen, and then organically, and with the hope that if you fix all of them, you'll have a very safe solution. But the challenge here is, you know, we are all working on long tail problems, and this is essentially, it's endless. And moreover, the world is an ever-changing place as well. So you'll always have new challenges coming up. Maybe it's because, you know, like a new trend on TikTok that suddenly happened, and suddenly, you know, everybody will dress up differently. So the question here is, can you find problems or issues like in a more proactive way, rather than waiting for them to happen? And note, this is orthogonal to, you know, everything we talked before, because here, this is about, recognizing and proactively recognizing problems that will happen. You know, all of those topics we talked before, be foundation model, generative AI, they still apply once you recognize what problems you are facing. And the second topic I want to mention is, you know, machine learning models are not, they don't have infinite capacity. You can do, and we don't have infinite data in our storage. I mean, we do collect a lot of, you know, all these self-driving car companies. We have a lot of data, but you can't store all of them. So what do you do? The answer here is continual learning, and I'll talk a little bit about that too. All right, let's dive right into them. Let's start with motivation. So this is, again, a video. I'll just play it in the background. It showcases all the challenges of, you know, well, at least a subset of challenges we've seen in San Francisco that are somewhat long tail situations. And these are things that we have to deal with in San Francisco. Essentially, you know, the question here is, it's great if we know that these exist and then we can tackle them. But the true question is, how do we get aware of these? How can we tackle them before they happen, before they cause us problem in the first place? Right. Perception side as well. So that I generate scenarios that will challenge our perception system. So we can start with a kind of baseline object that we can mine on the road and where our object detector has no problem with. But then we have to modify it in a way to another object that will cause problems to the object detector, and while keeping the object human interpretable as well. So, you know, just very related work, right? I mean, this really reminds us of the adversarial sample generation literature that has been around for at least 10 years, where the idea is you have an input, in this case was ImageNet, you have an ImageNet image, and you have a differentiable system, and you have a loss at the top, and you can compute the gradient from the loss with respect to the input image instead of the weights, and that gives you this noisy image that you can append or you can add on top of your input image, and suddenly the network will say, okay, it's a cat. So this is great, but it's difficult to use it one-to-one in a self-driving application. So this is equivalent to saying, okay, here we just modify, we have this point cloud scenario, we just modify a few points here and there, and suddenly the entire perception system fails. But this is not particularly useful. Think about it. You give it to like a perception engineer. What are they supposed to do with this? They just look at this, okay, this is very overfit sample of their system failing. So it's not particularly helpful for them to understand the weakness, the true systematic weaknesses in their system. So what we came up with is essentially to say, okay, we need to regularize a lot in this pipeline. So if we were to do, you know, the traditional adversarial generation, it will be just like this part. So the right part, right? You have a detector that's differentiable, you have an input scenario, and just propagate the gradient back. But you have to do more than that in order to make the system useful for the perception engineers. And well, the answer is just to regularize the model in several ways. So one way we found out was to just make this scenario compositional. You can compose the scenario. So you still have a concept of, you know, here, you know, what is a background, what are the active agents, and you know, where is the self-driving car. So that certainly helps with regularization because it projects the entire scene into a lower dimensional space. And the other regularization is in this shape, right? So you know, we still need to have, you know, shape, you know, like an asset to render in the scenario. And if you just take the assets as like a bunch of point clouds or meshes, it will still overfit. You'll just have small changes in the assets, and that will fool the model, the detector here. So basically, we need to rely on a much lower dimensional latent encoding in order to regularize the model. All right. So and then the challenge is once you have this structure, the next challenge is, okay, this entire thing needs to be differentiable. And how do we do this? We rely on some existing works. So here is a prior work called deep SDF, so sign distance function. And what it does is it trains a function to represent the asset. So when you have like 3D assets, you can represent as a mesh, and represent as voxels, or you can represent a function. So we found that with mesh and voxel, it's difficult to make a differentiable. But if you have a function to represent the assets, it's kind of naturally differentiable. So the beauty here, right? You basically need to train this assets, like given a bunch of point clouds, you can now train this function that represents this rabbit here. It's differentiable, watertight, and it's very easy to render this object as well in a differentiable way. So yeah, exactly what we do, right? You have a car, you train the SDF function on top of this car, and the SDF essentially says, okay, given a latent code and given a point in space, 0 would mean that like a point that's on the surface of this asset will have the value 0. And I think if it's positive, it's inside the object. If it's negative, it's outside of the object. So then what you can do is you can encode. So the next thing you need to do is to render this car from the view of the self-driving car. And the rendering parameter, you can just play with the calibration. It's essentially rotation translation, right? Or essentially linear transformation that you can apply to the rendering parameter theta. And we can do some simple ray tracing here. So for example, a point that's outside of the car, you can just reuse it from the existing log. And if a point is somewhat occluded, because you get this from the function that we learned before, you can then replace the occluded points with the points that's on the vehicle. So now what you can do is to insert objects into a logged scene. So this is a scene that we have in the data set. And now you can easily render this object in a differentiable way anywhere in the scenario. So it's important it's differentiable for the adversarial generation procedure that we'll do later. Okay, cool. So now we have the entire pipeline figured out. What now to do is to optimize so compute gradients of the loss with respect to the shape encoding Z and the pose encoding theta, and then you can find adversarial samples that are helpful for the perception system. Yeah, exactly. So you can generate shapes that will drop your accurate detector accuracy to 0. You can also find poses that will. So by poses, we don't just send a car like to the outside of the range of the sensor. That would be too easy. So even for pose changes, we just keep the object where it is and just make small changes in rotation and translation. So yeah, here is, for example, an original asset that we can then that's easily that can be easily detected, and then we can use this method to generate something that looks like a convertible. And obviously, there are still challenges in there are still questions. Okay, how realistic are these? There's no windshield. There seems to be a hole here. But overall, it gives engineers a direction what to look for. For example, here, in San Francisco, there aren't many convertible cars. So, this basically points the engineer to a direction. Okay, we might have some trouble if we go to a place where people are super rich and everybody drives a convertible car. All right. So, and now the beauty here is also that you can apply the gradient at different levels. So you can, gradually, because the gradient is essentially a direction that you walk on in this latent feature space. So you can apply it at different degrees. For example, you can, so essentially that can help you to generate a gradient of different assets. And they, one after each other, they will just achieve lower and lower scores for the object detector. So I wanted to reemphasize the results shown here are not based on our production model and the production object detector. So this is reproduced on a benchmark data set, on set of benchmark data sets, and using a publicly available detector. That's certainly, hopefully that's good than our own. So here are some examples of, you can take an SUV, you can apply this method on a particular scene. And for example, it will give you kind of human interpretable weaknesses in this procedure. So we see like objects with smaller windshield, the detector has some trouble with it, or anything that's more sporty, but still looks legit. The detector also has problems with them. So the same with the shape, you can do this for poses as well. And here we just simply rotate the object, and already the system has started to have some trouble detecting object. So here again, right, same thing as with shape. So you take an asset, you place it somewhere in the scene, and where you get a very high detection score. But now just by playing with the simple like rotation translation parameters for the asset, you can find weaknesses on your detector. I think usually there's no question that, the detector is supposed to detect these objects, even if they're just rotated slightly and translated slightly. All right, so here are some quantitative results. So this basic attack, this describes attack success rate. So essentially what, so in each of the graph here, I know it's a little bit small to see, I'll just quickly describe it. The upper curves show the accuracy of the detector on the baseline objects, and the lower ones show the accuracy of the detector on objects that we've adversarially tuned. So then there's also the question of fidelity. And here, the experiments we conducted was to just add the generated objects as additional training data, right? If they belong in the same distribution, you expect an increase in accuracy once you do that. And this is what we observe as well. So we have baseline. So the blue line here is a baseline curve for on kind of the baseline objects. And once you fine tune the detector with the generated data, you get the green line, which is a somewhat improvement. And then the orange line is the accuracy on the generated data. And if you obviously fine tune, you see a much larger improvement. All right, so much to generation and adversarial finding problems proactively rather than waiting for them to happen. The next topic I want to touch on is continual learning. So here, the question that we all face quite frequently for the self-driving car industry is that you have to keep changing your model for new tasks or new ODD. So those are just when you go to another location, you have to include the data from the new location. You have to retrain your model. So this is, and you need to not forget the old data either. So we go to another place, you need to be good at the new place, but you can't forget what you learned at the older place either. So there are a few ways to do this in the literature. So one way is called multitask learning. So what you do is to simply add new data to your old data and you train your model in a multitask way. The problem here is that this is, it's very difficult to tune this system because you have to have a really great balance between the old and new data. And typically the new data is so small, tiny, that essentially you don't end up with any change. And that's not great. You have to, one way to do it is just to reweight the new data, but then you're in this regime of really careful hyperparameter tuning. So the other way, the more sophisticated way is called model anchoring. And here what you do is to take your, so you compute some statistics from your new data on the old model, and your objective becomes, okay, fine-tune this model while not moving too much away from the old statistics. The problem here is that it doesn't scale well if you need to do this fine-tune multiple times, and it has a high, it requires extra engineering as well, because you need to compute all these statistics and then set it up in your training pipeline. Now, basically, these are all complicated. So what people end up doing is just the simplest thing, which is to fine-tune with your new data with a lower learning rate, and then cross your fingers that nothing is going to blow up in our faces. Now, so the traditional fine-tuning is fine, but here I'll outline a problem that essentially the forgetting problem. So you start with a pre-trained checkpoint on your old data. You take your fine-tune steps here, 1 to T, and now you are at this new checkpoint. And the next step you want to do is, for example, going into this n+1 step. So you'll notice this is the source of essentially the forgetting problem, right? So you're kind of moving, there's no guarantee that you will stay. So this pre-trained checkpoint, let's assume it's pretty good on the old data, it's already fit on the old data, somewhere in a local minimum there. And essentially this leads to forgetting, because there is nothing that prevents you from just moving away from your old, a checkpoint that work pretty well on your old data, right? So this looks like a past learning problem again, right? Where you have two objectives, two gradients that you want to pursue, and what you can do is you can, so there's a kind of simple trick here that's well known, where you project the gradient from one to another, and that's the direction that you go. Now you might ask, okay, we are going back to multitask learning. So how is it different from what, this thing here that we said we don't want to do? So the main difference here is really that you don't need your old data. And that's very critical for self-driving. You don't want to store all your old data forever. So in case you want to fine-tune your model, you have to kind of use the old data again. So essentially what we did here was to trade a few steps. So I mean here, the cautious of you will notice that this is a little bit more expensive than before, right? You have to take n steps in order to take one step. So essentially what we did was to trade the fine-tuning efficiency against the need to store data. But typically, if you do fine-tuning, you don't need that much fine-tune anyway. So that's something that we are typically willing to sacrifice. So just quickly on the results, we have here a toy example where we are trying to fit a distribution, a two-dimensional distribution, like original data, new data, and we want to train on this new data without forgetting. So in the end, we want to model this full data set distribution. And if we were to do it on original data, we get something like this. And you'll see that fine-tuning on head only or the full model will give you something substantially worse than what we get with our fine-tuning approach. So which is also reflected in the quantitative measure. So we applied this on some other benchmark task as well. So this is CIFAR. This is a CIFAR variant that's targeted for long tail distribution. So there are there's a huge label imbalance in the CIFAR example. You have the old task. So we decided to just treat the common classes as the old task and the long tail classes as a new task. And in that way, we have this kind of continual learning setup with long tail classes. So what we can see is, we also played with the imbalance ratio, which is how tiny the long tail classes are compared to the common classes. And we see consistent improvements over all kinds of fine-tuning approaches that people typically do. Now, the last task was self-driving. I mean, we're a self-driving company, so we have to apply it for self-driving applications as well. So here is a prediction task where the old task is to do motion forecasting on vehicles, and the new task is to do motion forecasting for pedestrians. So we want to train one model that does both at the same time. And we first trained it on cars, and then we wanted to extend it to pedestrians. And again, we see kind of consistent improvements of this. So the baseline here are the fine-tuning baselines, and good fit is the model that we have. So the cars would be the performance on the old task, while the bottom ones are performance for the new task, and we can see consistent improvement as well. All right, so just to wrap up today's talk, so I highlighted a few. First, I highlighted a few research opportunities for industry and for academia. I hope to inspire some of the future works from all of you. I highlighted 2 works on proactive risk mitigation and continual learning. And I think there are still a lot of challenges. In particular, I really like the line of foundation model and generative AI. And the challenge I see here is that people typically talk about precision. So when ChatGPT gives you a result, you just look at, is this feasible? Does it make sense? But there's a lack of study on kind of model distribution. So people don't question, okay, what other explanation are there? I think, Alex earlier talked about a few examples where he asked ChatGPT how to drive. Actually, we've tried that too. And a lot of times it doesn't give you the right diversity of answers. So I'll wrap up here. We're still hiring. And if you want to tackle some of these challenges with us, we'd love to hear from you. All right, thank you.
Take our time, we will take one question. Yes.
Thank you for your presentation. Give us the practical situations. May I ask you a question? Because right now the car industry, they are thinking about the software-defined vehicles. So is any particular situation you need to think about the different structure? So how to use the traditional data to fit in the new structure?
Sorry, may I clarify a little bit? What does software defined?
Because
structure?
right now they use the like the as before they for the automotive electronics they just use ECU, so they can one-to-one. But right now they are going to another structure, so domain structure. So if they use a domain structure, maybe they use 6 domains. So one is for the navigation. So I don't know if we use a domain like a traffic situation, so they will use this kind of data to fulfill the real situation for the new cars structure.
Are you asking how we are trying to extend to multiple platforms, or?
Yes, because you mentioned about we need to use a new structure data, but how can we collect? Because we accumulated the traditional data for a long time. So if we want to fit in the new car structure, so is any particular things we need to solve the traditional data structure going to the new data structure?
There's probably some domain adaptation and sim to real situation to handle. But overall, I think it has been studied before, and this is something that we can all try the baselines on first.
Okay, thank you.
All right, thank you.